Gauss law is commonly used to find out electric field in certain cases where there exists a symmetry in the charge distribution. Now let's see what symmetry of charge distribution means. Basically, there are three types of symmetry. We'll discuss this with a few examples. Now this first thing which we are concerned with, the first type of symmetry is symmetry about a point. It's also called spherical symmetry. Now in this whole space there is a point O. Now we are considering that there exists a symmetry about this point. Symmetry about this point means all the points which are equidistant from this point O, they have similar charges or equal charges. Let's elaborate it a bit. Now suppose we are taking a point P which is at distance R. So all the points which are at distance small r from this point P, they lie on the surface of a sphere this way. They all will have same amount of charges. This. Here we have considered a spherical surface of radius A. Now all these points on this spherical surface, they are at equal distance from this symmetric point O, so they have equal charges. Here we can say that there is some charge density when R, the distance from center, is equal to A, and if R has any other value other than A, then there is no charge density or no charge at any point. So here you can express the charge density in terms of distance R from the center. This way, sigma means charge density is 0 when R is not equal to A for any other distance which is either greater than A or less than A. And on this surface there is charge which is distributed uniformly. So charge density is Q by the area. So here we have expressed our charge density in terms of distance R. And this is example of a symmetry about a point or spherical symmetry. There could be other examples even. Instead of having a single spherical surface, we can have two or more spherical shells. Just see this example. Here we have two concentric spherical shells, one of radius A having charge Q1, the other of radius B with charge Q2. Here even you can say that there are charges only when distance R is either A or B, and if distance R of any point is neither A nor B, means maybe the point will be at over here, so R is less than A, or over here R is in between A, or over here, anywhere other than R equal to A or B, there will be zero charge density. Let's express that in form of equation. For R equal to A means at distance A on this sphere the charge is equally distributed, Q1 charge, so the charge density is Q1 by this area. For R equal to B over here, again charge is equally distributed, so it's Q2 by 4 pi B square. And for any other value of R, the charge is 0. We can even have a solid sphere with uniform surface uniform volume charge density inside it, this way. Here even there are charges at every point and equal charges at every point for r less than a, and no charge for r greater than a. So in all these examples, we are able to write the surface charge density or the volume charge density in terms of distance r from the center. And the most important thing, charge densities are equal at all points which are equidistant from the center or the symmetric point. So if you take a sphere of any radius with that symmetric point as the center, then charge on all points of that sphere will remain same. So this was about charge distribution with a spherical symmetry. Let's see what would be the pattern of field. In all such cases where there exists symmetry about a point, the field will be directed along the radius. It could either be towards the center or away from it, depending on the nature of charge. But one thing is sure, that the field will be along the radial direction. Let's see this. In this case, what will be the pattern of field? This first case, this would be the pattern of field. Let's see our second example, concentric spherical shells. Here also the field pattern has to be the similar one along the radius, this way. Our third example of that solid sphere with uniform volume charge density, this one. Here even same. So all cases where there exists a spherical symmetry, the field lines are directed either away from the center or directed towards the center. This is the field pattern. Next, there exists symmetry about a line. In all such cases, the charge density will depend only on the perpendicular distance from this line of symmetry. So there are several examples of this cylindrically symmetric charge distribution. The first being a very long wire with uniform charge density on it. Then you may have a very large cylindrical, very long cylindrical shell. Anyhow, first let's see the field pattern in this one. Here the field lines will be directed away, perpendicularly away from this line of symmetry, this way. Let's come to the other example, the cylindrical shell one. This is a cylindrical shell having uniform surface charge density. Here even the axis of the cylinder will be the line of symmetry. Field pattern will again be same, this way only, perpendicular to the line of symmetry, this way. So there could be many other cases, like very long coaxial cylinders, cylindrical shells, or very long solid cylinder with uniform volume charge density inside it. So this was the case of cylindrical symmetry. The last one is symmetry about a plane, this one, and we'll just discuss its example. This is a very large plane sheet having uniform charge density on it. We could say that there exists symmetry about a plane only if the charge density depends on distance from this plane. This is an example of symmetry about a plane. The field lines in this case, they will be directed perpendicular to this sheet. In this upward direction, the field above this sheet will be directed upward, and field below this sheet will be directed downward, this way. So we have up till now discussed the field pattern in various cases of symmetric charge distribution. We would be using this to find formula for electric field in certain symmetric charge distribution cases. We'll discuss this in some examples.